Good day, I'm Maile Madziba. Welcome back to our channel. Today we're continuing with our CRR 211, which is the second year chemical engineering module at the University of Pretoria. We continue with the study guide examples, and today we're looking at example 3.5.1. It says, compare the estimated energy required to heat 1000 kilograms per hour of CO2 in a flow process from 673 Kelvin to 1473 Kelvin if the pressure remains constant at 100 kilopascals using two different correlations for the heat capacity of CO2. Now it gives us information here that the information that we're going to be using to do the correlations, to do the comparison of the correlations. It says from Himmelblau, which is the textbook that is used at CIR 211 at University of Pretoria. It says from Himmelblau, the heat capacity of CO2 in kilojoules per kilomole Kelvin and temperature in degrees Celsius is Cp is equal to 36.11 plus 0.04233 T minus 2.887 times 10 to the power minus 5 T squared plus 7.464 times 10 to the power minus 9 T cubed. Now it then brings the Perry. Says from Perry, the heat capacity of CO2 in calorie per gram mole Kelvin and T in Kelvin is Cp is equal to 10.34 plus 0.00274 T minus 195500 over T squared. So basically what they are saying here is that we're going to calculate the change in energy of heating 1000 kilograms per hour of CO2 using two heat capacity equations. The first Cp, we're going to be using the one from Himmelblau, which is Cp is equal to 36.11 plus 0.04233 T minus 2.887 times 10 to the power minus 5 T squared plus 7.464 times 10 to the power minus 9 T cubed. And they are telling us that this heat capacity has units of kilojoules per kilomole Kelvin and T in degrees Celsius. So another thing I just want to briefly explain is that you see the units have Kelvin, but the temperature that we're going to be using is actually degrees Celsius. Why? Because we are told that the T in this equation is actually in degrees Celsius. And as for why that gets to happen, that we use degrees Celsius but then we get units of Kelvin, that is CIR 123. I did some countless examples based on that, where we actually explain and just explore why is it that we get to have units of Kelvin, whereas we plugged in degrees Celsius in the equation. So, and then we come to the Perry, which is Cp is equal to 10.34 plus 0.00274 T minus 195500 over T squared. Now, the heat capacity of Perry is in units of calorie per gram mole Kelvin, and T is in Kelvin. So in Perry, there isn't really much to explain there. So the first thing that we're going to be doing for us to be able to do that, we're going to choose a basis. And as usual, an easier basis to use is actually the basis that we've already been given, which is 1000 kilograms per hour CO2. 1000 kilograms per hour of CO2. Now, another thing we're going to start with the Himmelblau, right? Now, when you check the units of Himmelblau, of the heat capacity of Himmelblau, you realize that the units are in kilomole, but then we are given, we have our basis as 1000 kilograms per hour of CO2. So which means for us to be able to use this equation of heat capacity from Himmelblau, we need to at least use kilomole instead of kilograms. So the first thing that we're going to be doing is to convert the kilograms, 1000 kilograms per hour CO2 into kilomole per hour of CO2. So as usual, number of moles of CO2 is equals to 1000 kilograms per hour multiplied by 1 kilomole all over 44 kilograms. This is actually the molar mass of CO2. Then now that we have cancelled the kilograms, it's much easier to work with seconds, so we're gonna convert the hours to seconds. So we know that 1 hour is actually 3,600 seconds. 3,600 seconds, and if you use your calculator, that's gonna give you 0.0063113 kilomole per second. So we're gonna be using the kilomole per second for us to be able to get that. So now, one thing we know that the change in energy, or the molar change in energy, it's actually N delta H, right? And this N delta H, for you to get N delta H, is to integrate the CP. So we're gonna be integrating the CP. We can put the N here because it's a constant, it doesn't change. And then now we go to, in the CP from Himmelblau, we know that the temperature is in degrees Celsius. So, but we are given in Kelvin, so we just need to make sure that we use degrees Celsius instead of the Kelvin. Why? Because we are told that these are the units and the temperature is in degrees Celsius. So with that said, then we know that we're going to be integrating from 400 degrees to 1200 degrees, and we plug in the CP. You know the CP is 36.11 plus 0.042333 minus 2.887 times 10 to the power minus 5 t squared plus 7.464 times 10 to the power minus 9 t cubed. Don't forget to put dt because we are integrating with regard to the temperature. So now, with that said, when we integrate all that, well, the n is still a constant. You can actually even put in the n already here as this much, but I'll just put it at the end. So when you integrate all this, you know that the 36.11 becomes 36.11 t, right? Then plus this one becomes it's 0.04233 t squared over 2. Well, that's mathematics. There's calculus. It should be clear by now. So minus 2.887 times 10 to the power minus 5 t cubed all over 3, right? So, and then coming here becomes plus 7.464 times 10 to the power minus 9 t to the power 4 all over 4, right? The dt is gone because we have integrated already. So with that said, then we know that we're gonna be sorry about my camera. My stand is not so stable today. Yeah. So now we know we're gonna be integrating 400 degrees to 1200 degrees. So this is basically the integration. Now when you substitute the values, you can always say 0.0063113, right? I don't need to put the values. And then we get to our 36, we say 36.11, and we do our normal math. We know 1200 minus 400, right? And then we say plus, we go here, we say 0.042333 all over 2, and then we have 1200 squared minus 400 squared, right? and then we go to, let me just take it a little bit higher. So, and then when we get here, we have our, here we have this one, which becomes minus 2.887 times 10 to the power minus 5, right, all over 3. And then we have our 1200 cubed minus 400 cubed. Well, there's no space for that, so I'm gonna put this down here. And then we have plus, is it visible? Yeah, we have plus 7.464 times 10 to the power minus 9 all over 4 into 1200 to the power 4 minus 400 to the power 4, right? And we know that all these are in a square bracket, and from here all through here to here is multiplied by this. So as soon as you've done that, so we can just use your calculator there, because they no longer are variables, so we only have numbers. So you can just use your calculator. Let me bring back the page down here. You can just use your calculator and, sorry, let me just put my paper well so that it's clearly visible. Yeah. So you can just say, therefore n delta h is equals to, n delta h is equals to 276.44 kilojoules per second. So this becomes our kilojoules per second. Just to explain something here, the reason why is that is because, you know, when you have, yes, the heat capacity, and then you integrate it, and then you multiply also by the n, which is the number of moles, then you're gonna have kilojoules per kilomole, rather kilojoules per second. And basically then the what you call that, the change in energy is actually, you know, kilojoules, right? And then because we have multiplied the it's actually kilojoules per kilomole, but because we have multiplied this energy with n, then we get our kilojoules. However, the second comes from a position where, because we're given our basis as 1000 kilograms per hour, right? So which means if there wasn't an hour here, we're going to have a final answer of kilojoules. But then our CO2 is actually given as 1000 kilograms per hour. So there's a time factor that we also need to consider. So this is basically their change in energy. Now, when you come to okay, remember our issue here is to calculate to compare the change in energy of the two CPs, one from Himmelblau and the other from Perry. So now we are done with the one from Himmelblau. We come to the one from Perry. So I can say, let me just write here that Perry is Perry's handbook for chemical engineers. So we can just say, do the same thing and say n delta H is equals to n. Now we're gonna need to integrate, but when we check the CP of Perry, we are told that the temperature is in Kelvin, so we're gonna be integrating in our temperature in Kelvin. So, and we know that is actually 6 is from 673, is the same temperature but now in Kelvin, 673 Kelvin to 1473 Kelvin, right? And let me just put in the CP of Perry. It's 10.34 plus 0.00274 T minus 195500 all over t cubed. That is actually, yeah, and then we have our dt, right? So already we have our number of moles. We don't need to do, okay, well, let me check here. You see our, in Himmelblau, our number of moles was actually expressed as kilomole, but in Peri, when you check the calculation, the units, you realize that they're actually in gram mole. So what we need is just to convert the number of moles from kilomole per second to actually gram mole per second. So then we say number of moles CO2, right, is equals to 0.00631313 kilomole per second multiplied by 1000 gram mole all over 1 kilomole. So if you use your calculator, that becomes 6.31313 gram mole per second. So we just cancelled the kilomole and now we're using gram mole. So this is actually the number of moles that we're going to be using in the CP of Himmelblau. And that we can just say, therefore, delta H is equals to, let me just put it here, 6.13, sorry, it's 6.31313, right? And then we integrate 673 Kelvin to 1473 Kelvin, and we have 10.34 plus 0.00274 T, and then minus 195500 T to the power minus 3, and we can just say, let's just do this and say dt. So I actually just converted the t, the over t squared over t cubed to t to the power minus 3, so that I can find it easy when I integrate. And if you do your integration, then we have our 6.31313. When you integrate this, it gives you 10.34 t plus 0.00274 t squared over 2 minus 195500 t to the power minus 2 all over 2. No, this is actually a positive here, because when you're going to mathematically, when you're going to integrate, you're going to have minus 2 here, and then minus 1 is going to be minus 3. So the 2 and 2 going to cancel, you're going to be left with the negative, right? And yeah, and then we know that we integrate from 673 to 1473. Now that is equals to 6.31313 into, so we start here 10.34, and then we know the temperature, it starts from 1473 minus 673, right, plus 0.00274 all over 2 into 1473 squared minus 673 squared, right? And then we come to the third one, and then we have, it's minus, let's see, well, how do I put it? Let me just, yeah, so it's plus 97750. The 97750 is actually 195500 divided by 2, and then we come here, we know this is actually we know t to the power minus 2 is actually 1 over t, 1 over t squared. So this is actually more mathematical now. So I guess you guys are familiar with that. So we have 1 over 1473 squared, right? Minus 1 over 673 squared, right? And then we still have the square brackets for the sake of the number of moles. So now when we get here, we are left with the numbers, and we can just use our smart calculator. So just a normal calculator, and then the total answer that we get here is actually 67069.72 calorie per second. So that's actually calorie per second. However, here we actually found from Himmelblau we found our energy in kilojoules per second. So for better explanation, for a better comparison, we just need to convert this to kilojoules per second. So we're gonna say is equals to 67069.72 calories per second multiplied by, we know 1 calorie is actually equals to 4.187 joules, so we can just say 4.187 joules all over 1 calorie, right? And then that is equals to 280820.91764 joules per second. Now if you convert joules per second to kilojoules per second, you just divide by 1000, so you have our 280.8209176 kilojoules per second. So this actually, we have actually done comparing the two equations, the change in energy from the two CPs. So from Himmelblau we have 276.44. They are estimates, of course, but you could see they are very close. They are actually less than around 4 kilojoules per second difference. So then this actually brings us to the final. This actually concludes our example 3.5.1. So thank you guys for your time, and I hope we meet again in our next video.